Good morning, everybody. This is Mark Wilder. I'm an application engineer at Yaskawa America, Inc. And today we are going to give you an introduction to conveyor tracking. Key word of this is introduction. This will be only an introduction. We are going to talk about the basics of how the MC track conveyor belt function block works, but we do already have planned a more in-depth webinar, and that will be entitled Practical Application of Conveyor Tracking with MotionWorks IEC, and that'll take place in the new year. So without further ado, let's begin. And let's begin at the beginning. What is conveyor tracking? Well, this is our conveyor tracking function block. It is the MC track conveyor belt. And this is how we are going to initiate conveyor tracking. What conveyor tracking does is it creates a relationship between some sort of mechanism like a robot or a delta robot and a conveyor belt. At its heart, what it does is it creates a moving part coordinate system. You're going to hear a lot of acronyms during this, and we'll try to make sure that they stay straight in your mind, but a part coordinate system, or PCS, for the items on the conveyor. This PCS makes it easier to move to a part by letting the controller keep track of its position relative to the group. Again, we're going to be talking about all of this stuff more in depth as we go. So the result is a superimposed motion in the X direction of the conveyor belt over whatever the mechanism's commanded movements already were. Let me give you an example of that. Let's say this is our situation. I have a part, that's the red box, on a conveyor belt. The conveyor belt's moving from left to right. I also have a delta robot, and it needs to track that part. Well, if I use MC track conveyor belt, what's going to happen is that delta robot is going to move in the X direction of the conveyor. Doesn't matter where the delta robot is. It could be halfway across the room. It could be anywhere. And it will still track that conveyor in the X direction of the conveyor, the forward direction of the conveyor. That's the tracking move. I can use standard move function blocks to do a linear move. So if the conveyor belt wasn't moving, I would just say move down to 0, 0, 0 of the part, and it would move down and do that. So that's my downward move. The resultant is going to be, if we command that downward move and we have MC track conveyor belt active, the result is going to be this vector move that is a sum of the two other moves. So we have a linear move telling us to move downwards. We have a tracking move telling us to move along the X of the conveyor belt. And the result is going to be a kind of diagonal move where it's tracking the conveyor belt and moving down. Now, before we can really talk about conveyor tracking, we need to wrap our head around coordinate systems. And it can be a little bit complicated, but I think this discussion will help us out. So here I have just some sort of work cell in my factory. I have a robot, I have a delta robot, I have a conveyor belt with some parts on it, I have a pallet off in the back that I want to move those parts to, and I have a bunch of different ways that I can look at where all of these things are located. The top level would be the world coordinate system. So that's a system that just exists anywhere in the world. It's very arbitrary where it exists. We could put it at the base of the robot. We could put it anywhere in this room. But I've chosen just arbitrarily to put it at this corner of the conveyor belt. So that's the world coordinate system, and I can tell you where any of these things are in that world coordinate system because it's 3D space. Each of the mechanisms will then have their own coordinate system, and we call this the MCS, or machine coordinate system. Now, the world coordinate system we don't program in too much, but the MCS, the machine coordinate system, is one of the main ways that we program moves. In fact, the MCS is the base of the group. So all of the other coordinate systems are going to be referenced in reference to this machine coordinate system origin. It's a little arbitrary about where it is in that it could still be anywhere in the room, but typically it's somewhere towards the base of the mechanism itself. So here we show it at the base of our robot, the machine coordinate system. But of course, that's not the only machine coordinate system because we actually have two machines in this case. So we also have the machine coordinate system of the Delta robot. Now, one thing you may notice is that the z-axes are inversed, and actually so maybe are the x and y-axes. Looks like the x-axis is going in the same direction, but the y is completely inversed. So all of these are going to have different offsets to a world coordinate system, although the world coordinate system is going to be the same in reference to itself. So each of these machines has its own machine coordinate system, and each of these are going to be commanded separately. Now, the result of this on the robot, if we look at the machine coordinate system, after it goes through kinematics, we're going to have yet another coordinate system, and this is another one that's kind of done in the background, but we don't actually program directly in it, and that's the tool plate coordinate system. So as I move this robot, its machine coordinate system origin is going to be the same, but this tool plate coordinate system is going to change relative to that. It will always be at the end of the mechanism. We need that so that we know where the end point of that mechanism is so that we can define a tool. And once we have a tool, which in this case is a manifold with some suction cups on it, then we have a tool coordinate system. So the tool plate coordinate system moves with the robot. The tool coordinate system tells us where the tool is relative to that. In this case, it's just out front of it by however wide that part is. The end result is something that we're very much going to be talking about a lot, and that is the tool center point, or the TCP position. That is going to be where we are moving. When we say move to a certain MCS position, it's the tool center point that's going to be moving to that MCS position. When we say move to a particular part coordinate system, it's going to be that tool center point, or TCP, that's going to be moving to that position. So that's kind of the output of all of the kinematics and the tools that are on there. Now we have more coordinate systems. Each of these parts will have their own coordinate system. It's called the part coordinate system. Here you can see we even have some different orientations. The PCS3 is actually rotated a little bit, so it's going to have a different X, Y, and Z axes compared to the others. So this brings us to our first pop quiz. I have these two part coordinate systems, or two parts, I should say, moving down a conveyor belt. You can see the X direction of the conveyor belt shown. One is rotated, one is not. So how does the X-axis of these part coordinate systems change as they travel down the conveyor? I'm going to give you just a few seconds to think about that. Well, the answer is they don't change. The part coordinate system is tied to the part. So even if it's moving down the conveyor, its part coordinate system axes relative to the part is always going to be the same. And that allows us to do a move like to 0, 0, 0 and actually track that part as it moves down the conveyor. The 0, 0, 0 of the part is going to always be on the part. So I show three part coordinate systems for the parts themselves, but there actually is another part coordinate system in here as well. And that is on our palette here in the background. So that part coordinate system will kind of be fixed in world space, but it again allows us to do moves to put these parts as they come onto that palette. So we will be in one PCS to pick up the part, we'll change to a different part coordinate system to put down the part. There is one more coordinate system that we don't have to deal with too often. It's dealt with behind the scenes, and that is the axis coordinate system, or ACS. And what this is the individual positions of each of the motors that's on the mechanism, on the robot or on the gantry or whatever. Typically, we don't need to worry about that because they are each, the kinematics take care of what the axes need to be at. So that is a separate coordinate system, however. So just to kind of reiterate here, kind of from the broadest view, is the world coordinate system. That's kind of a single point within the room. We have machines that are offset from that world coordinate system, although the actual machine coordinate system is the base for each of these groups. The output of a particular machine will give us a tool plate coordinate system. That is where the end of the mechanism will be as we move. And then we offset that with a tool coordinate system that tells us where the end of the tool is. And that end of the tool we call the tool center point, or TCP. And then each of our individual parts will have its own part coordinate system, PCS. One last thing that's not really a coordinate system, but that we're going to need to know in order to do conveyor tracking is, of course, the direction of travel of the conveyor. That's shown by this arrow here with the X. So where can I see all of these coordinate systems? Well, when we define a group, it creates a group axis reference, which is a huge structure that contains a lot of different information. And each of these coordinate systems have their own substructure to tell you the commanded position, velocity, acceleration, and the actual position, velocity, and acceleration of each of those group coordinate systems. For axes and machines, these are vectors that have up to 32 degrees of freedom. So, you may have a robot that has, 7 or 8 motors on it. Each of those will be represented in a single structure. The world, part, and tool coordinate systems are in 6 degrees of freedom, X, Y, Z, RX, RY, RZ. And you can see that there is actually an extra variable for that we call the offset. And that is an offset to the machine coordinate system. So each of these coordinate systems, the world coordinate system, the part coordinate system, and the tool coordinate system, will have their own offset from the machine coordinate system. There's a bunch of other very useful things in the axis group ref structure as well, but we're not going to discuss those in these particular slides. So let's talk about how we're going to use our MC track conveyor belt function block. Before we start, I just want to point out that we've actually created a quick reference guide. We're not going to go over it, what you see right now, but it does exist. It's on our website, and if you search for conveyor tracking or quick reference guide, you'll find this single sheet quick reference guide that when you're starting to use conveyor tracking, you may find helpful. It is available now on yaskawa.com, and you can see what the document number is there. But again, if you search for conveyor tracking or quick reference guide, you should find it. All of the things that are on that sheet we're going to discuss here in this presentation. So here I have, my situation kind of like I showed earlier. I have a part on a conveyor belt. I have a robot that's going to track that part. And I have a sensor that's going to sense the position of that part. So the function block is shown in the upper right-hand corner. It is the MC track conveyor belt function block. The first thing I'm going to need to define in order to use this function block is what axis group I want to be part of this relationship, and what the axis is for the conveyor belt that's going to be part of this relationship. Next, I'm going to need to define the origin of the conveyor belt so that I can establish an offset between the robot and the conveyor belt. And we call this the conveyor belt origin. So in this particular case, I am showing it right under the sensor, so in the middle of the conveyor belt. So we would put in some numbers to show us what that offset is between the machine coordinate system and the conveyor belt origin. That's in 6 degrees of freedom. It's a vector. We're going to actually show a little bit of a practical example later that will put numbers on that, but in this case, you can see where it is. The next thing I'm going to need to define is the initial object position. This is the position of the part when at the recorded position. We haven't got to the recorded position yet, but that will be coming soon. But this is the position of the part relative to the conveyor belt origin at the recorded position. So if we have a camera, that's going to show us a lot of, it may show us multiple parts, but in the case of like a laser sensor, as soon as that sensor activates, it will capture that initial object position. So we have another pop quiz for you. Based on what I just told you, if I set my initial object position to 0, 0, 0, 0, 0, 0, and I trigger this MC track conveyor belt, where is the origin on that part? Where is the origin of the part? Take just a few seconds to think about it. Well, I said that the origin of the part is relative to the center of the conveyor belt origin. So if I have 0, 0, 0, 0, 0, 0, then it must be right at the conveyor belt origin. Which brings up another pop quiz. What if I don't want it there? What if I want it at the base of this arrow? This kind of may be a little bit confusing here, but I want the origin to be right here in the middle with the x-axis along the same x-axis that the conveyor belt is traveling. So this is my origin here at the base of that arrow, following along the x-axis of the conveyor belt. Now what would I set my initial object position to if the box is 10 by 10 by 10 units and I want the center to be at the top of that box? Again, I'll give you just a few seconds to think about it. Okay, well, if our box is 10 by 10 by 10 and we need to set as an offset to our conveyor belt origin, then in the x direction, we need to go back 5 units, 5 in the reverse direction of x, 0 in the y direction, and 10 up in the z direction. This raises a couple different questions, and we're going to have another quiz coming up, but how do I know which direction is the positive y and the positive z? That's a question that's perfectly valid to ask. So now we have the same situation, but we want the x to be in a different direction. Now I want the x to be as shown by the arrow on the top of the box. So again, I want the PCS origin to start from the center of the top of the box, but now my x direction has changed. So how would I do that? And again, I'm going to give you just a few minutes to think about it. Okay, well, with our pop quiz here, let's talk about how we define these coordinate systems. You can do a web search and read more about this if you want. We're going to cover them in a little bit of detail here, though. If you do a web search for the right-hand rule for coordinate systems, you'll find some drawings similar to the ones I have here. So we start with the direction of x, y, and z. Now, I expect all of you right now have your fingers making this same shape. Your index finger will be if it's pointing in the x direction, then your middle finger will be pointing in the y direction, and your thumb will be pointing in the z direction. So if we rotate our hand to move it so that the x is in the same direction as the conveyor, we can see that positive y is actually kind of in the same direction as the orange arrow on top, and z is moving upwards. Now the reason we need to know that is because we're going to have to introduce a rotational aspect to our offset. So here's the directions of y and z that we just figured out. So now we need to know the other right-hand rule, which is that if your thumb is pointing in the positive direction of an axis, your fingers will curl in the positive direction of rotation around that axis. So again, thumb pointing in the direction of the axis, your fingers will curl around in the positive direction of that axis. So if we look at this box, we need to rotate it so that the x of the conveyor belt, we need to rotate it around the z-axis so the x of the part coordinate system is the same. So using that, we should find that our initial object position, the x, y, and z parts of that are exactly the same, -5, 0, and 10. That gets us to the middle top. But in order to get the x direction changed, we need to add that rotational element into it. So we have 0 in the rx, 0 in the ry, and 90 degrees in the rz. So those are two different right-hand rules that are very handy to remember in order to get your positive directions of a coordinate system, in order to get how a rotational axis works about a particular axis. So depending on how your parts come down this conveyor belt, your initial object position will have one of these types of answers as a recording. If you had a vision system, then it may create its own initial object position. What we have found doing our vision systems is that we can put in a an offset to the conveyor belt origin, and it will automatically give us initial object positions for whatever the vision system detects. The next thing we're going to need to define in conveyor tracking is the area where we want our synchronization to occur. We call that the sync zone. This is going to be defined by two different inputs of the MC track conveyor belt function block. The first is the start distance. That is the distance from the origin of the conveyor belt to the beginning of the synchronization zone. And the same thing going to the end of the synchronization zone is called the end distance. So those are both just scalar numbers. So we have a start distance along the x-axis and an end distance along the x-axis of the conveyor. This does not tell us everything we need to know about that synchronization, however, because we know that we can't instantly synchronize. So we have to have a defined area where we can begin synchronization and a defined area where synchronization will end. So the kind of a sync in zone and a sync out zone. And those are defined in the input to the function block called track options. We're going to talk more about those on the next slide. The next thing is the recorded position. So that is the position of the conveyor belt when the track conveyor belt function block is executed. So it's just like a trigger that you would use with an MC buffer or anything else. You set up your trigger and you capture the position and you put that in as the recorded position. Now typically this is also the time when we execute the MC track conveyor belt. We have a part now. We have all of the information we need in order to begin tracking. There was a question that popped up about the conveyor belt origin. Is it defined as an XYZ position offset or as the resultant vector offset? It is a vector that you put in, similar to how we discussed the right-hand rule and how part coordinate systems work. It's the same kind of offset. So you have an XYZ element and an RX, RY, RZ if you need to rotate it. Again, we'll have a practical example coming up, but we can see in this particular case, if the conveyor belt is in the same XY plane, then there's definitely going to need to be an RZ element to that because the X directions between the machine and the conveyor are not going in the same direction. So that covers everything in the MC track conveyor belt except for that bottom input, which is the execution mode, and we are going to talk about the execution mode in this discussion, but not on this slide. So these are the inputs to the MC track conveyor belt function block. Before we start, we have to define the conveyor belt origin, the start and end distance and track options of the synchronization zone, the initial object position, and then and the execution mode. And then once we're ready to go, we'll put in our recorded position and execute the function block. The sensor does not need any sort of special latch. Once you set your latch and you detect that position, the latching function will give you the recorded position that you can enter here. All right, so let's talk about these track options. And again, the track options define our synchronization zones, our sync in and our sync out zone. For purposes of this discussion, we're mostly going to talk about the sync in zone. So here I have an overhead view of a conveyor belt. The conveyor belt origin is shown, and you can see that the start distance is defining where the beginning of that sync zone is. So conveyor tracking may start when you hit the conveyor belt origin, but the actual synchronization is not going to start until the part gets in that green zone, that synchronization zone. So the track options at its top level has three different elements to it. One is the sync in, which is going to define how the sync in works. One is the sync out, which is going to define how the sync out works. And then we have track scaling. And if there's a difference in units between your conveyor and your mechanism, then this is what you would use in order to take care of that. So let's talk about our sync in zone. It has its own set of its own structure to define it, and it is called the Y track sync in options. And here are the elements of that particular structure. So the conveyor distance is the amount of distance that the conveyor is going to move during synchronization, not the tool, the conveyor. The mode is what I wanted to talk about first, and it's an enumerated type that has 4 options, 2 of which are actually supported at this time. The two that are supported are the master distance and the within range. If we choose master distance, then that means the synchronization will begin at execute. Of course, we'll wait till the part passes the start distance. SD in this case stands for start distance. And it will finish at conveyor distance later. So if my part is already in the synchronization zone when I execute this MC track conveyor belt, essentially what I've done is I've shifted my sync in zone. It's going to be the same distance every time, but it may start later. The opposite of this, or the other option, is within range. This means that we'll begin at execute and finish at a fixed conveyor distance past the start distance. So if our part is already in the zone when we execute this, it doesn't matter. We still have to have it done by the time it reaches the end of this synchronization sync in region. If it's way close here at the end before we execute it, then that means we're going to have to move very, very, very fast, or we're going to need to come up with a way to tell the system that it's too short of a distance and to abort. And we'll get to that in just a second. The other two, elapsed time and Excel limited, are not supported at this time. So now I've added something to our little picture at the top, and that is the TCP. Take a couple seconds and see if you can remind yourself what TCP stands for. It stands for Tool Center Point. So this basically is showing where the tool is when we begin this track conveyor belt execution. We then have to define how far that is from the end of the sync zone with the value TCP distance. So in this particular case, as it's shown on the screen, the conveyor may be moving 10 units and the TCP distance may be 5 units because it's starting in the middle. We're going to talk more about that as we get going as well. In the event that we're using within range, we talked about how if the part gets too close to the end of that sync zone, we might just want to not try to catch up to it because it would have to go too fast. And we call that the minimum sync distance, or min sync distance. And again, that's number of units from the end of the sync in. The sync out, which is not going to be shown on the screen, has the only one element that's really of use, which is the conveyor distance. And that is how far the conveyor is going to move while we sync out. It will always, the tool, if we get to the sync out zone, will always stop halfway through. So let's talk about these track options just a little bit more and what what difference the TCP distance makes to our movement, to our speeds of our tool. So in this particular case, again, I have an overhead view of a conveyor belt and my sync in distance is 10 units. If I start right in the middle of that with a TCP distance of 5, on the graph at the bottom, you can see how that's going to work. It's going to slowly accelerate, get up, and match speeds of the conveyor. This is the default situation. If I don't put a number in for TCP distance, it's going to assume I'm starting at half of the conveyor distance. If I start farther back, it's perfectly allowable, but of course, because it's starting from a dead stop and the conveyor has been moving the entire time, that means that we are going to have to overspeed in order to catch up with the conveyor. At the end of the sync zone, we will still be at the conveyor speed. It's just that we're going to have to move faster than the conveyor to get there. The third option is if we have a short TCP distance. So here, my TCP distance is 2. This means I have a long time to sync in, and it may actually even cause the tool center point to go backwards before it goes forward to catch up on speed. Ideally, optimally, you'd want it right at that halfway point. That gives you the most time to catch up without overspeeding the conveyor. And that is also the default case. Next thing we're going to talk about is execution mode. If you remember the MC track conveyor belt inputs, execution mode was that one that I decided to talk about later. Now is that time. There are 3 options for the execution mode of MC track conveyor belt. They are immediate, delayed, and queued. In this particular case, what I'm showing at the top is that we have a move that's executing right now, and we have a bunch of other moves that have already been buffered. What this is going to then show us is, depending on which one of these situations we called MC track conveyor belt, when is it actually going to become active? So not surprisingly, if I call MC track conveyor belt with immediate execution, it's going to become effective immediately. So if I'm in the middle of this active move and I say MC track conveyor belt execute with immediate execution mode, it's going to start immediately. Delayed will actually start as soon as the active move is finished. Then the MC track conveyor belt superimposing will begin before the next buffered move is started. That's delayed. And the last is queued. And what that means is it puts it at the end of the stack. So it goes after the last buffered move and will start before the next move that is put onto the motion queue. Of course, all of these also require that the part has passed the start distance and that we're in the synchronization zone before the execution of MC track conveyor belt actually begins. So this is our execution mode. It determines when MC track conveyor belt will begin to take effect and when the superimposing of the conveyor position happens. The next thing to discuss is, when will conveyor tracking be canceled? So I've established a conveyor tracking relationship. How do I end that relationship? There are 4 different ways that can happen. First is I can just do an MC group stop. That'll bring the group that's doing the tracking to a complete and total stop, and it will break the relationship of conveyor tracking. Next, I can use this function block Y group set frame offset. Now what this function block does is it defines different coordinate systems and the offsets from the base coordinate system, the MCS of the group. If I define a new part coordinate system manually, then conveyor tracking will be canceled as soon as I make a move in that newly defined part coordinate system. If a PCS move is currently active and I try to do this, then the Y group set frame offset function block will give an error. I cannot do it while a PCS move is active. The third way that we can cancel conveyor tracking is to do a MCS move, a machine coordinate system move, with track conveyor belt active. So here at the top, I'm showing a motion queue. So I have an MCS move that's currently active, and I've already buffered another MCS move. And then I've queued up MC track conveyor belt, so that at the top where it says MC underscore TCB status, that's the MC track conveyor belt status, and that means that tracking is active. So as we go down this motion queue, I'm going to complete my 2 MCS moves. I am going to start conveyor tracking, and then my mechanism will be moving along with the x-axis of the conveyor belt. I can do a couple PCS moves, maybe to pick up a part. But as soon as I command a new MCS move, a move in the machine coordinate system, it will break the relationship between the mechanism and the conveyor belt. So an MCS move, when track conveyor belt is active, will cancel the conveyor tracking. You'll notice that the MCS moves that I called before conveyor tracking was active did not cancel the pending track conveyor belt. And the last way that you can cancel conveyor tracking, sort of, is to start a relationship over. So in this particular case, I have MC track conveyor belt part A happening, and then I call MC track conveyor belt again. So the relationship is broken between the first one and started between the second one. So in this particular case, we're still conveyor tracking, it's just we've switched between the PCS is defined by the first MC track conveyor belt and the PCS is defined by the second MC track conveyor belt. Of course, we can see at the bottom of this motion queue that we have another MCS move that happens, which will cancel that relationship of the second MC track conveyor belt. The next thing that we can discuss are the outputs of the MC track conveyor belt function block. And the outputs are shown at the bottom here: execute, busy, active, in sync, and done. There's also a group parameter that we can read, parameter 2251, that we call track state, that will tell us what part of tracking we are doing. Oh, and we have a pop quiz. And that pop quiz is, how do you read this parameter 2251? Doesn't really have anything to do with conveyor tracking, but we're trying to keep you on your toes. Well, 2251 is a group parameter, so you read it by using Y group read parameter. You put your parameter number in as 2251, and the resulting track state will be given on the value. Pretty straightforward. So if we look here, we can see that that track state before we execute tracking, just to help you visualize this, there's a little blue box that's on the conveyor belt that we're looking at on the top, and it's going to be moving from left to right. And when it hits these particular lines, how does that change the states of these things? So before we call MC track conveyor belt, of course, all of the outputs are off, and the track state is inactive. It's 0. As we move past the conveyor belt origin, we have now begun conveyor tracking, but we're not to the sync in zone yet, so we call this track state 1, or waiting. Execute and busy are now true for the MC track conveyor belt function block, but it is not yet active, and it is certainly not in sync. Once that part gets to the sync in zone, then our active becomes true. So we're execute, busy, and active are all true. Our track state is 2, syncing in, but we are not yet in sync, so that one is still false until we cross, or until we end the sync in period. We cross over into the sync zone, then we know we're in sync, and the in sync output comes on as well. Normally at this point, we would use that in sync output to execute maybe some PCS moves or actually perform some sort of operation on the part that we detected. But if we don't, then eventually the part will make it into the sync out zone. At that point, the in sync will go back to false. And if the part happens to go all the way through that sync out zone, then the done will come on. And the busy and active will go false. So let's give an application example. First, what I'm going to show you is what happens if I don't do anything during conveyor tracking. So I'm going to call this an idle tool. I'm not going to do anything except execute conveyor tracking. How is this going to work? Well, first, let me explain what we're seeing on the screen. I have a part that's shown as a big blue box. I have a camera that's going to be my my sensor in this particular case. I have a tool that's waiting at the middle of the sync in zone. You can see my MCS origin is shown there as well. That's where the, like, say, base of the robot is. And I'm also showing the track state there in a nice big number that we'll see the purpose of in a second. But how am I going to fill in this MC track conveyor belt function block so that we get a good conveyor track? So we're going to go step by step through that. So the first thing I'm going to need to do, I've already defined my axis group as the group that we're moving. I've already defined the conveyor belt axis as axis 3. And now I need to define my conveyor belt origin. Again, the conveyor belt origin is the offset between the MCS origin and whatever we want to define as the origin of the conveyor belt. In this case, it's the big yellow cross. So we can see that maybe in the X direction, maybe we're negative 25 units. In the Y direction, maybe minus 10 units. Maybe the conveyor belt's a little bit higher than the MCS origin, so I have a positive Z in there as well. And then a rotation around the Z-axis that defines the fact that the X directions are pointing in different directions. So that might be an example of a conveyor belt origin. Next thing I need to define is the beginning and end of my synchronization zone. So I can put in my start distance just as a fixed number. I can put in my end distance just as a fixed number. So in this case, I have a total of 100 units from the conveyor belt origin, but we're not going to start until 10. So the total synchronization distance, including the sink in, the sink, and the sink out, will be 90 units of the conveyor. I need to define that sink in and sink out zone, and I do that with track options. So again, defining the sink in zone, track options structure, the sink in substructure, conveyor distance. The conveyor is going to move 10 units. And my TCP, since I'm starting in the middle of that, will move 5 units. That's the second line. I want to use mode master distance, which means if I happen to start and the part's already in the sink zone, then the effective sink in is going to move along with that part. And on the output side, I still need to define a conveyor distance, and that is going to be 15 units. If we're still in conveyor tracking, when we hit 100 minus 15, so 85 units from the conveyor belt origin, then we will begin syncing out. Next, I have to define the execution mode. This tells us when we begin our conveyor tracking. In this case, we're just going to start it immediately. All right. In this case, because I have a camera, I'm not going to actually know what the initial object position is until that camera triggers and figures out what the initial object position is relative to the conveyor belt origin. So what we're going to see in the animation is that blue box is going to move from the left to the right, and when it crosses that conveyor belt origin, the camera is going to take a little snapshot. It's going to fill in the recorded position, it's going to fill in the initial object position, and it's going to execute MC track conveyor belt. All right, so this first time through, again, I'm going to run this animation several times. The first time through, just pay attention to the relationship between the part, the big blue box, and the little red circle with the blue cross in it that represents our tool center point. All right, so let's take a look at this. There, we trigger it. Once we enter the sync zone, now our part begins, and it's going to be all in sync all throughout the sync zone. And normally here we would do some sort of MCS move, but we didn't. So our tool ends up coming to a stop as the part moves all the way down the conveyor belt. All right, so let's take a look at that one more time. This time maybe while watching that, you can keep an eye on the track state. That's that giant number in the upper right. I tried to make it big so you could watch it while it's moving. So here, before we execute it, we're in track state 0. And as soon as we get past that track conveyor belt, we go into the waiting stage. That's track state 1. Now we're trying to sync in. That's 2. We're in sync. That's track state 3. And once we hit the end of that sync zone, we go into track state 4 that we're syncing out. And as soon as the part exits that sync out zone, we go back to track state 0. Let's look at that one more time. This time we can look at the outputs of the MC track conveyor belt function block. So they're going to turn on and off as this part moves. So right now all of them are off. As soon as we execute it, the busy will turn on. And now we're active because we're beginning to sync in. And once we get to the sync in zone, the in sync output comes on as well. And it turns back off once we hit that sync out zone. Once we get out of the sync out zone, we go to done. Our conveyor tracking is done. So that's a very simple example of what would happen if we execute MC track conveyor belt and we don't do anything during that actual synchronization. Again, normally during the synchronization, we're going to be doing some sort of PCS move to pick up the part or stamp the part or maybe spray some glue on the part or something. But if we don't, this is what's going to happen. Let's take a look now at a practical example. This one's not going to be animated in the same way. But we're going to be doing a kind of a flow chart to tell us what we're going to do if we want to do, let's say, gluing. So this part is going to come, again, the blue box, and the tool, the red tool, is going to, once we're in sync, it's going to dispense some glue onto the top of this box. So we're starting our dispenser off at the spot that we specified in track options. Now you'll notice in this particular case, instead of being in the middle of the sync-in zone where we have been starting, now we are at the beginning of the sync-in zone. You may recall what that means is that the tool will have to overspeed in order to catch up to the part. There's nothing wrong with this. It's just something you're going to have to be aware of. It'll end up going twice as fast as the conveyor. So we go to the camera, we capture a position. Somehow the part went under the origin. Now we've loaded that initial object position into our MC track conveyor belt, and it begins to move down. The tool is waiting, and eventually we'll catch up to it. And now our track state has become 3, so we know that we're in sync. Now separately, I have some sort of function block that's looking for that, and as soon as it sees that the track state is in sync, then it will begin dispensing the glue. So it goes green when the glue has begun to dispense. That process takes however long that process takes, so maybe halfway through that synchronization zone, the dispensing is over. And at this point, I can break my tracking relationship by sending my tool back to the beginning while the part continues to move down the conveyor belt. Right, that's an MCS move. So because it's an MCS move, that cancels conveyor tracking. And at that point, I am ready to start again. So here's a simple example of using conveyor tracking without any like external moves, moving you to a different a different region. We're going to show that example next. This is just moving back and forth along the conveyor belt. Let's actually look at it one more time, a little quicker. So again, our part's coming down the conveyor. Our dispenser is already at the beginning of the sync-in zone because that's where we specified it would be. The part moves down the conveyor. Its position gets captured. We execute MC track conveyor belt. Once we get into the synchronization zone, we begin our sync-in process, and at the end of that, we will be in sync. Then we execute a separate command to begin dispensing. That does not break the relationship. So they're still tracking together while it's pouring out that glue. At the end of that process, however long it takes to dispense that glue, we can stop the dispensing and do an MCS move back to the beginning while the part continues to move down the conveyor. And our last example is going to be a pick and place example. Still going to be very simple, still just one part at a time coming down the conveyor. But now what we want to do is we want to take that part and we want to put it on a pallet. That's the little blue square up here that's already got a few parts listed on it. Up here at the top. So, in order to do this, the first thing we want to do is we want to move do an MCS move to move our tool, our TCP. Do you remember what that stands for? Tool center point. Move our TCP to the beginning of the synchronization zone. And as the part comes down, we trigger our track conveyor belt. We again wait for the synchronization to occur. This is exactly the same as before. And now as it's moving, we are going to do a downward PCS move. So we'll do a little pop quiz here that's not part of the presentation, but what position do we command for our move? So I want to move down to pick up that part. What position do I command a move to? The answer is, assuming that I've set everything up right, that would be 0, 0, 0 of the PCS. So if I do a PCS move to 0, 0, 0, because I'm tracking, it will move along the x-axis of the conveyor while tracking, and it will also do a downward move to pick it up. So in this particular case, my tool is now green, which means I have a hold of the part. It's going to continue to move down the conveyor belt. Now I lift it up. It would actually still be tracking in this case. So even as I lift it up, it's still going to be moving along the x-axis of the conveyor because PCS moves do not cancel tracking. But now when I want to move it to where it goes, I am going to do an MCS move. And once I do that MCS move, now I have canceled tracking. And now I can do another MCS move to set down the part and release it. And then lift the mechanism again and move back to the beginning so that we can start all over. So again, we'll run through that one more time quickly. We start at the beginning of the synchronization zone. As the part comes down, we capture its position. We set the initial object position and the recorded position in the function block. Now we're waiting for it to get in sync. So it gets in this in sync zone. Here our track state, parameter 2251, has become 3. That means we're in sync. And now I can command a PCS move to 0, 0, 0 that is going to move the tool down to grab the part. Then it will continue tracking as it lifts the part. And then an MCS move to our drop-off point will cancel the tracking relationship. And then I can release the part and get ready for another go. This is the end of the prepared presentation. Don't forget that we do have a more in-depth and kind of with more examples and more kind of real world how we're going to apply this in a webinar coming up on January 15th, 2018 called Practical Application of Conveyor Tracking with MotionWorks IEC. One question, does the MC track conveyor belt need to be run in a fast task or same update rate as the as Mechatrolink? The answer is no. It can be run in any task, similar to the way we do linear moves. Once we call it, the firmware, or the what we call the motion kernel, handles the execution of it at that point. So it doesn't really matter what task you execute it in. The motion kernel is going to take care of it once it's executed. So it doesn't need to keep going back to that conveyor belt to execute. The next question is, can you track incoming and outgoing conveyor belts at the same time? The answer is yes. You basically are going to keep calling MC track conveyor belts in order to kind of break the relationship between one conveyor belt and begin the relationship with another. When you do this, what you're going to have to keep track of is your recorded position, because it may actually be the same between executions of MC track conveyor belt. But if you think about two parts coming down a conveyor and a camera capturing them, then you can do your move on the first one. Again, the camera will typically provide an initial offset or initial object position for you. And you can do whatever you're going to do with that first one, and then basically execute that same function block with the same recorded position and a different initial object position, and it will execute just fine. And then the final question is, how can you accurately find the conveyor belt origin? This is something that's going to be discussed a little bit more in the advanced webinar that we're doing in a few weeks. But the answer is it's typically taught. So typically you move your robot, line it up with the x-axis of the conveyor, and then we actually have a function block that will help you define that by defining the x direction and the y direction of the offset. So that's typically how you're going to find the conveyor belt origin. We very much appreciate your attendance. We hope this was helpful to you. And again, please remember that we have another webinar coming up in a few weeks, and you should see an invite for that probably next week sometime. Thank you very much.